Hi students, this is Dr. Spellman doing my first video lecture here for logic. Hopefully this goes well. If you have questions afterwards, feel free to reach out to me, or if you got tips, hints, any suggestions, those would be great. Alright, here we go. Today we're going to talk about rules of equivalence, and this is from chapter 10.4a in your book. This chapter gives us a number of rules of equivalence, 6 in all. The 6 that I've listed here: De Morgan's rule, or De Morgan's law, commutation, association, distribution, double negation, and tautology. So this order is a little bit different than the order in your book. That's no problem. The important thing is just that we're learning how to do these rules. Again, as a quick refresher, we talked about rules of inference the last couple weeks. What rules of inference do is they allow us to move from one or more statements to another that isn't logically equivalent to those from which it was derived. Rules of equivalence or replacement allow us to move from one statement to another that is logically equivalent to the statement from which it's derived. So the rules of equivalence are going to just use one line, and I know before that we had a few rules of inference that just use one line, but the rules of inference were actually getting something that's in a way simpler and less complex often. That's where there's an implication there. Rules of equivalence were just saying the exact same thing in a different kind of way. So first we're going to talk about De Morgan's. Let's look at an argument. So say someone was to say, it's not the case that both A and B are true, that Ada and Boston are in Ohio. We would symbolize that as I put it here on the right side, not the case, parentheses, A and B. Now this is logically equivalent to saying this thing, either not A or not B. So if we know that it's not the case that A and B here, we also know it must be either not A or not B. At least one of those has got to be true. It's possible that both are true. At least one has to be true. So these two statements are logically equivalent to each other. And we can go from this statement here, it's not the case that both A and B, to either not A or not B. And we can go back. So if we have it's not the case that A or not B, we can conclude that it's not the case that parentheses A and B. Similarly, if we know it's neither A nor B, it's not the case that A or B, that's equivalent to knowing that it's not the case that A and it's not the case that B. And again, we can sort of go both directions. If we know not A and not B, we can infer that it's not the case that parentheses A or B. So let's go ahead and look at how we might indicate the equivalence here. And what this is saying is that this statement on this side is logically equivalent to this statement on this side. So if we have a not and then in parentheses an and, that gets translated not P or not Q. The symbols change, right, from an and to an or, and then negation in a way like it gets distributed. Over here, if we have not parentheses an or, then we distribute in some sense the tilde, and the or changes to a dot, the and. Let's take a look at how this might show up in an argument. So say we have this argument. It's not the case that parentheses A or B, and we know that C and D are true, and we're trying to show that not A is true. So not A, we might think, how am I going to get that? I look over here. line 2 is just a distractor, right? C and D, that's not going to help me at all. But I've got A here, but it's stuck in these parentheses. I need to get it out. And the way that we're going to get it out of those parentheses is by using De Morgan's. So we take the tilde, we distribute it to the A, distribute it to the B, and then we switch the or to an and that gets us not A and not B from lines 1 De Morgan's. Again, if you think it's not the case that A or B, that's saying neither one of those things is true. So we know not A and not B must be true. And then if we're trying to get not A, we have not A and not B, we can just do simplification and conclude that not A is true. If we're going to try another one, we might start with A or parentheses, not B and not C. We've got not A on a line, and we're trying to conclude it's not the case that B or C. Okay. Now, there's maybe a couple ways to start. We could do disjunctive syllogism right off the bat. Right? We have A or, we've got this disjunction with A as the first disjunct. We know that not A is true, and so we could get the second disjunction. Or we could do it a little bit differently. We could just go ahead and do the De Morgan's right away in the middle of the proof. So when we do use a rule of equivalence like De Morgan's, we don't have to use the main operator or pay attention so much to the main operator. We can do it sort of within the line. So if I see that tilde B and tilde C, if I can see I can do De Morgan's on that thing in the parentheses there, I can go ahead and do it and just leave it how it is. I can say A or tilde parentheses B or C, and that's from De Morgan's. I'm trying to get not parentheses B or C. Got A or that thing. I can do disjunctive syllogism now and get to my conclusion. Tilde parentheses B or C. All right, that's our first rule, De Morgan's. It's kind of a trickier one because you've got to notice, oh, I've got tilde, tilde, B and C, and so I can pull that out. Or tilde, tilde, tilde B or tilde C, I can pull that tilde out front. It's kind of tricky, potentially hard to see. Note that you can't do either one of the following things. So we need this operator to change. If it's tilde A and B, it needs to be tilde A or tilde B. Same here. If we have not A and not B, we can't just pull the tilde out in front, put parentheses around it. We need to change the sign, so those aren't going to work. These two, however, down here, can we do those? No, same problem. If we're going to have the tilde out front, A or B, we're going to distribute it, we need to change the sign. And I'm saying distribute because that's sort of a common math term. That's maybe sort of how we would talk about it if it was negative in math. But we're going to have another rule called distribution, so I don't want you to get confused about that right now or later. But I'm saying distribute, but distribution in a logical sense is a different kind of rule, and we'll talk about that later. Okay, so commutation is another rule of equivalence. If we know that A and B is true, then we know that B and A is true. The order doesn't matter. This one's a little bit more obvious, a little less tricky. If we know that B and A, we know that A and B. So commutation is just switching the order of those two claims. Or works with or as well. So A or B, we know that B or A. If we know B or A, we know A or B. Simple enough. This actually works with the, oh man, I'm blanking on the name. The triple bar, the double-headed arrow, which is like an if and only if necessary and sufficient conditions. Shoot, not, it's not coming to me what that is. I have to sort of skim the book here and remind myself exactly what that operator is called. But sort of while I do that, I'll figure that out in a minute. Let's go to the one on the left. So this problem here, A or B. We know not B. We're trying to get A. Now, before, right, I had been telling you, let's try and just do disjunctive syllogism. We'll do commutation first, and then we'll do the disjunctive syllogism. So here, it's like I've got that B over there. I know not B. I know that A must be true. But if I can't do it over on the right disjunct, I need to flip the order. So that's what I'm going to do here. B or A. That's from line 1 commutation. And then I can do disjunctive syllogism from lines 2 and 3. So if I have B or A and I know not B, I know that A must be true. Again, that's 2 and 3, disjunctive syllogism. Here's another one. I've got tilde, parentheses, A or B. I'm trying to get not B. Okay, so here you're like, what am I going to do? Fortunately, we've learned De Morgan's already. If we have a tilde out in front of parentheses with an or an and as the main operator, we can sort of take that tilde, distribute it, right, to both sides, and then switch the operator. So that's what we're going to get. Tilde A and tilde B, and that's De Morgan's. I've got the tilde B over here. I know that's what I want to get. Can I just take it from there and put it on its own line? Well, I sort of know that I can do that, but I'd like you to show that you can do commutation, that rule, move that tilde B out in front, then we can simplify, take the tilde A off the right side of the conjunct there and get that's simplification to get our conclusion. Here are some things you can't do. If you have an arrow, you can't flip the positions of A and B. That's not equivalent. Same if you have not A and B, you can't just switch the order and leave the tilde where it was. Those things are not logically valid inferences. Here are some things you can do, though. If you have the double-headed arrow, right, an if and only if claim, necessary and sufficient claim, then you can switch the order there. If you have something inside parentheses, right, I can switch the order inside the parentheses. So it's also possible to just switch the entire thing. So here I have A or parentheses B or C. I can do commutation inside of it. That's what I've done here. Or I could also do commutation on the whole thing. So I could move this whole thing here out in front of the A. That's good. And then ors or ands, they all work. Here I've done the thing where I've flipped the whole thing over the main operator. So A and B and C. I haven't changed the order within the parentheses. I've just changed the order that they come in. We're going to move on to association. So with association, we're just sort of moving parentheses when we have the same connective, and it's an and or it's an or. So if I know A and B and C, then I know A and B and C. So when I've got this and, it doesn't matter exactly where the premises go. These claims are logically equivalent to each other, and so we can just flip where the parentheses are. We can shift them in a sense. Same with or. If I know A or B or C, then I also know A or B or C. And I can flip both directions, right? Shift. Maybe thinking about shifting rather than flipping is the better way to think about it. Okay, here are the sort of statements, the logical equivalents. On this question, I have A or parentheses B or C, and I'm trying to get C. I also know tilde. It's not the case. The parentheses, A or B. What am I going to do? If I could get the parentheses around A or B and parentheses, then I could do a disjunctive syllogism using line 2. And so I'm going to use association to shift where those parentheses go. So from line 1, where's my little cursor here, if I can find it? From line 1, I've got A or parentheses B or C. I'm just shifting those parentheses over one to get line 3, that's association. Again, I need it to be or on both the main operator inside the parentheses, the main operator of the entire statement. Both need to be or, and then I can do association. Once I've done that, I can do disjunctive syllogism to get C. Here's another one. If I have A and tilde B, arrow C, and I have A and parentheses, not B, and D, I'm trying to get C or E. So E, that's new. That's not in the proof at all. We know that we're probably going to need to add that on. What I'm trying to get is C. Well, to get C, I need A and not B. In order to get that, I need sort of the A and the not B together. I can use association to get those two together. I just shift the parentheses over. So A and tilde B and parentheses and D. That's from 2 association. The next step I do is I simplify to get A and tilde B. Once I have that, I can use line 1, use modus ponens to get C, and then once I've got C, I can add on E. You can't do association with the arrow. That is not going to work. You also can't do association if the operators are different. If the one inside the parentheses is an or, the one outside is an and, or vice versa. If the one inside is an and, the one outside is an or, association won't work. You can do something with this, distribution, but we can't do association. So those are not valid. They're not good inferences because they're not equivalent. You can do these. So if you have the double-headed arrow, then you can shift the parentheses on that. And if you have like knots, tilde, tildes interspersed in here, that doesn't matter. What matters is that you have or as the main operator outside the parentheses, or as the main operator inside. That same connective there, then you can shift the parentheses as long as it's not an arrow, right? Okay. Moving right along, distribution. So if we know A and B or C, this is telling us A is true and at least one of these two is true. That's equivalent to saying A and B are true or A and C. Now it's possible that all of these things are true, but this is saying A and at least one of these two, and this is saying A and B or A and C. Maybe both of those, but those claims are going to be logically equivalent to each other. Ada in Ohio, and Boston is in Ohio, or Cleveland is in Ohio, right? It guarantees this. Ada is in Ohio and Boston is, or Ada is and Cleveland is. And we can go back to A and B or C. Now, this one here, the top one, has the and as the main operator and the or inside. But if it flips, right, if the or is the main operator and is inside the parentheses, that we can do that too. It's going to look a little bit different, but we can do distribution here. So if I know Ada is in Ohio, or Boston is in Ohio, and Cleveland's in Ohio, know that one of these sides is true. A is true, or B and C is true. If I know that, I know Ada or Boston and Ada or Cleveland. So let me think through that again. It's going kind of fast, even for me. So Ada's in Ohio, that's true, or both B and C are true. Now this down here is made true by the fact that Ada is in Ohio. And insofar as Ada is in Ohio gets distributed A or B, that's going to be true. And A or C, since A is true, that's going to be true too, so it's all true. If A was false, right, Ada's in Michigan, then it would have to be that both of these are true, and if both of these were true, then it'd guarantee that this side was true, and since the C was true, it'd guarantee this side is true. So that's logically equivalent. Again, it can flip back either direction. Now, we're going to want to be able, this is a tricky one to see, right? This is a pretty tricky rule. It's hard to maybe notice. What we're looking for is we've got an and outside the parentheses and an or inside, one in one place, a different one in the other, right? Association, we were looking at the same one in both places, and an and, or an or. Distribution, we're looking for an and in one spot, an or in the other. Again, down here, or outside and inside. Maybe what's even slightly harder to see is when we've got parentheses, we want an or in both and the opposite as the main operator, or an and inside both as an or as the main operator. If we find something like that, we can do distribution. But again, it's going to be harder to see. It takes more practice doing it to see it. Our rules, right, are getting more complex, more complicated, harder to notice, and that's why practice is just so important here. You're not going to be able to get a hang of it without practice. Okay, so we've got lines 1 and 2. We know that we're probably going to have to do distribution here, right? So we can look out for it. Can we do distribution on line 1 or line 2? Think about that. We can do it on line 1, right? We have the and outside the parentheses, the or inside. That's what we're looking for to do distribution. And it's important to notice how distribution works. So we've got something like this. And so when we use distribution, we're going to get something like this. The and, right, gets distributed in a sense. P and Q, or becomes the main operator. So notice the main operator switches. P, main operator, and Q or R. That becomes P and Q, or P and R. So the thing that's the main operator in the first statement is not the main operator in the equivalent statement. So if we take 1 and we do distribution, we're going to get A and B, n parentheses, or A and C. Now we're looking to get A or C. How are we going to do that? It's less obvious. One thing we know, right? We've got 2, right? Tilde, parentheses A and B. We've got a disjunction. If I know that the first disjunct is false, I can do disjunctive syllogism to get A and C. I can take the A. I need A or C. I can just drop that C off, right? Through simplification. And then once I've got A, I can just add or C onto it. So that's that proof. Here's another one. Again, we're probably going to have to do distribution somehow. We can look here and we can say, oh man, we've got two parentheses, got an and as the main operator, and an or as the main operator within those parentheses. So I can do distribution on this. Ignore line 2, right? That's not important for us right now. We've got something that looks a lot like this right here. And so we're going to get this. What's the term in common, right? The A. We need that common term too. I think that's an important thing. It's not just something in parentheses with an or and something else in parentheses with an or. We've got to have that one of those terms in common. If the P were over on this side, right, we could do commutation to move it onto the left side and then do distribution. So here we've got A is that common term. We've got two or claims conjoined with the and. If we do distribution, we get the and out front. And again, the main operator changes. So we got the A out front. The main operator is changed from an and to an or. And then parentheses B and C. Again, the thing that starts as the main operator moves inside the parentheses. Now we know not A from line 2. Again, disjunctive syllogism. So one thing you'll notice with a lot of these, we're doing disjunctive syllogisms. Before, we were looking at modus ponens, modus tollens, hypothetical syllogism, using those a lot to get the conclusions we want. But disjunctive syllogism can be really helpful here, and it's something we're going to use with some frequency. So here we get, using lines 2 and 3 in disjunctive syllogism, we get not B and C. We're looking for C. We can't take it out of that spot since it's the second conjunct. Let's use commutation to flip it around. Then we can drop the tilde B off because it's an and. That's simplification, and we've got our conclusion. Here are some things you can't do. A arrow, parentheses, B and C. The arrow is not going to work with distribution. Over here, this is maybe less obviously problematic, but A or parentheses B and C. The problem here, you'll notice, is that or is the main operator in both of these. So we've distributed wrong. If this down here at the bottom was A or B and A or C, that would be correct. But as we've done it here, it's not correct. And down here you might think, well, the double-headed arrow works a lot like and, we can do commutation around the double-headed arrow. I was even thinking that this, intuitively it seemed like, oh, that probably works. But I did the truth table and I saw that definitely does not work. So you can't do that down here at the bottom either. You can't just say, oh, the double-headed arrow will work just like an and or something like that. So those all don't work. The one that does work, we get the check mark before we get the example. So this, what's going on here is something like a little bit more complex, right? It's got the same structural form, but if this is P, this whole thing is Q, and this is R. So what I'm going to do distribution is A or this whole thing, and as the main operator, A or D. And vice versa, right? If I had this thing down here, so, oh, I've got A is common, both ors conjoined together. I could move back up in